All right, here is an example for using rotating frame equations to solve for different kinematic quantities. So it's a made up example. Here I have a pipe, and the pipe is turning about its base, and there's a ball inside, and somehow with, I don't know, linear encoders, for instance, inside the pipe, I have measured that when the ball is at square root 2 meter from the base, it has some velocity and some acceleration, and these velocity and accelerations are measured relative to the rotating pipe. And I know how the pipe is rotating, so it has some angular velocity of 2 and angular acceleration of 1. So the question is, what is the absolute velocity and acceleration of the ball at the instant when this angle is 45 degrees and all other quantities are as stated? So this is kind of a familiar example. You would expect to see this in earlier chapters too. One way you can think of it, you have a lot of good information about the angular motion, about the motion in radial direction. So it's perfectly suited for a polar frame. So if you want to translate these information to polar frame, so polar kind of thinking, you know, for instance, r is a square root 2, r dot is 1, r double dot is what, 2, and similarly theta is given 45, theta dot is 2, theta double dot is 1. So this is all the information you need to use the polar equations to solve the velocities and acceleration of the ball relative to the ground. And feel free to do that, but we want to use our other new formulation, which is pretty much the same, just you would expect almost all the polar terms to show up, but it is a more general framework than basically can be applied to any situation. If there is a rigid body or there isn't, if there are points attached to stuff or not, it is completely arbitrary. So rotating frame thinking. If I want to translate the knowns of the information to the notations that we need for the rotating frame. Rotating frame, everything is in vector form. So in this game, I have to assume some rotating frames. I'm going to take, I didn't put enough space for my frame. So let's take this capital XY as my absolute frame that doesn't turn. For the rotating frame, I need to pick a kind of frame that makes the most sense. And for us, the one that is best suited for this problem is the one that one of the axes always tracks the location of the ball, the other one perpendicular to it. So as the pipe turns, this little XY frame turns with it, and X is always pointing to the location of the ball. So with these two frames, I can write the vectors of my velocities and accelerations and everything. So let's see what we have. I know, let's start with position R. And remember, you have choices. So let's call this, be more specific. Let's call this A, the ball B, R of B relative to A. So our choice is either write this vector in the big XY frame, which will be 1 big I plus 1 big J, or alternatively I can write it in the little ij frame, in the coordinates of the rotating one, which in this case will be 1 square root of 2i, little I. As long as both are perfectly fine, as long as for the entire solution I am consistent with one of them, always either write all vectors in little ij or big ij, I should be fine. Pick one, stick with it. So because the rest of my information, specifically the velocity and acceleration given, those are relative to the pipe, they are easier to write in the little ij frame. So I stick with this one. From there, we also have velocity. But note that this velocity in the terminology that we need is velocity of B relative to A as observed by an observer that sits on the pipe and turns with the pipe. So this one is 1 I. Similarly, the acceleration that we are given is acceleration of B relative to A, again as observed by the pipe dweller, and this one is 2I. And again, note that I could write both of these as what? Square root 2 over 2I plus square root 2 over 2J, big J. Both are valid, but for some reason I want to decide to not use big IJ. I want to use little IJ. So these are those. I ran out of space, so let me add a bit of space. The other things we need are, well, we have and we need to translate, are the angular motion. Note that as the pipe turns with angular velocity of 2, the frame turns with the same rate in the same direction. And in our notation, to distinguish whether a body is rotating or a frame is rotating, we use capital omega to denote rotation of the frame, just a notation. And this one is the same as that omega, but I need the vector form, and in this direction, it is in the positive, it was 2k, positive k direction. Radians per second, and my omega dot, instead of using alpha, we use big omega dot to denote the angular acceleration of a frame. That one is in the same direction, magnitude 1 in k direction, radians per second square. It is given, so let's keep it, but I don't think we will need it because kind of that information is already encoded. Is it? Kind of, yeah, maybe not. Theta is 45 degrees, or I don't know if we don't need it, but let's write it as pi over 4 radians. All right, this is all the knowns of the information written in the language of rotating frame. Now let's get to solution. And we need to find absolute velocities. These are vectors. And I expect that when I solve the solution, solve the problem, the solution will be in the little xy frame. They are still absolute velocities, but those vectors are expressed in the little ij components, which if you want, you can convert to big ij if desired. All right, so solution. Let's start with velocity. I know absolute velocity of excuse me, of B. I can write it as absolute velocity of the base of the frame, V of A, plus the effect of rotation of the frame, omega cross R of B relative to A, plus whatever now this rotating observer is seeing, V of B relative to A as observed by this xy. And I have all the quantities. Noting that we didn't explicitly mention this, but the base, the way we chose it, it was our choice to keep the base at the fixed hinge. So this one, A doesn't move in the absolute frame. So that is 0. What I have is omega cross R, which is 2k cross R of B relative to A. Why did I take it as square root 2? I wasn't thinking it straight. It's okay. Square root 2. No, I don't like it. Let's take it as just regular 2, not the square root. So this will be 2i. This will be 2 square root 2. I'm just fixing some. 2j, and we don't need this. Okay, that's better, easier. So this multiplied by 2 little I plus my V of B relative to A, I calculated it to be 1I. So I do this because I never remember. K cross I is J, so I have 4J plus I. So write it nicely, more nicely, I plus 4J. So this is absolute velocity of B as expressed in the little ij frame. So if I want to draw it again, so this is little xy, and when I am here, this is the ball. The velocity is 1i and 4j. So this is the velocity, which if you know, for instance, little I, it has some components along big I and big J. You can convert this to velocity vector expressed in big XY frame, but we don't need that. This is enough. So this is 4, this is 1. Okay, that is that. We can do the same thing for acceleration. Acceleration of B is acceleration of A, acceleration of the base, plus a bunch of terms that are related to rotation and angular rotation, rotation velocity and what do I say? Acceleration in rotation. What am I saying? So we have a whole bunch of terms. The first one related to acceleration of the rotating frame, R of B relative to A. Kind of, we can think alpha cross R. plus you have some centripetal form, omega cross r. This is kind of r omega squared. You have your Coriolis, which is 2 omega cross v of b relative to a. But this is the one that is observed by the rotating observer. What am I missing? I have 1, 2, 3, 4, one more term, and that is the relative acceleration that the observer sees. A of b relative to a as observed by this xy frame, little xy. As before, point A is fixed, is our center of rotation, so it doesn't move. Acceleration is 0. And the rest is putting the numbers. Omega dot is k cross r of b relative to a is 2i. That is the first term. Plus omega 2k cross 2k cross 2i. Second term. I have 2 omega 2k cross v of b relative to a, that was I, plus the relative observed acceleration 2i. This part, k, this is 4, k cross I is j, and that makes it easier. So here, now the first term becomes this 2j k cross I plus, now I have 2k times 4j, that is 8k cross j is minus I, plus I have 4k cross I, another j, plus 2i. And all of this is, all the i's I have, minus 6i, plus 6j. Ooh, such a happy coincidence. Meter per second square. And this is the acceleration of the ball in the absolute frame, but expressed in the little ij frame. So when I'm here, my acceleration is minus 6i. We kind of expect that because as we are rotating, we have that kind of strong centripetal acceleration, which was kind of because of this, it dominated other term. And plus 6j. So this is my acceleration. So all right, this is the example using rotating frame. If you kind of match all the terms in the solution with what you would expect to come out of the polar equation, you would see there's almost a one-to-one match between all the terms. And yeah, you could solve this particular problem using polar. But as I mentioned, this rotating frame is extremely general purpose, and you can apply it to any situation, any problem, as long as you properly set your frames. So that's the end of this example. I will see you sometime later.